Hello everyone, my name is Erik Smistad and I'm from SINTEF Medical Technology and Norwegian University of Science and Technology. I'm going to talk about FAST, a framework for high-performance medical image computing and visualization which uses Opencl. First of all, medical imaging needs high-performance computing and visualization. And to show you why, I will demonstrate some of the data we have in medical imaging. Images acquired in computed tomography and magnetic resonance imaging are essentially 3D images. And here are some examples. At the right, we have a chest CT visualized with raycasting and showing a tumor in one of the lungs in green. Here we have a bone surface extracted from a CT scan, and here we have a slice of an MRI scan showing a brain tumor in green. Now these images are quite large. Typically, a size for a CT image can be 512 times 512 times 700 voxels. In digital pathology, we are looking at digitized microscopy images of tissue samples, which you see an example of at the right here, where you can zoom in as far to see the actual cell nucleus. Scanning at 40 times magnification, these images are huge. We can have sizes of up to 200,000 times 100,000 pixels, which results in an uncompressed image size of around 50 gigabytes. For most computers, these images can't even fit into the RAM. So we have to use virtual memory and tiled image pyramids just to visualize these images. In ultrasound, the images are typically much smaller, but ultrasound images are captured in real time, typically with a frame rate between 10 and 50 frames per second. Usually we want to process and visualize the results in real time, as shown in these two examples. At the left, we have an example of measuring the pumping efficiency of the heart automatically using neural networks while scanning. At the right, we're scanning the arm and automatically identifying blood vessels, nerves, and bone in real time using a handheld ultrasound device. We see an increasing trend in ultrasound where the devices are becoming smaller and using mobile phones and tablets for computations, which require even more efficient computation. Ultrasound is typically two-dimensional, but three-dimensional ultrasound also exists, where several volumes per second are streamed in real time. In 2013, we decided to create a framework which made high-performance computing and visualization of medical images easier by using less code, handling image memory transfers for the developer, and providing several common GPU-based processing and visualization algorithms. Efficient mainly by utilizing a dedicated GPU, but also integrated GPUs and multi-core CPUs. The framework should be open source and cross-platform, both in terms of operating systems, Windows, Linux, and Mac, and processor vendors such as AMD, Intel, and NVIDIA. 10 years ago, there was very little GPU image processing support in existing image processing frameworks used in medical imaging, such as OpenCV and the Visualization Toolkit, VTK, and the Insight Toolkit, ITK. Only a few algorithms were implemented for the GPU, often in an ad hoc way, which was not always easy to use and often entailed many CPU to GPU transfers. So our solution was to create a new framework from scratch, which we called FAST. Instead of being an optional feature, in this framework, GPU processing will be the default, and CPU-GPU transfers would be avoided. And to achieve this, we decided to use Opencl instead of the then more mature CUDA, since CUDA was not cross-vendor. We also decided to use Opengl for visualization since it is cross-platform. FAST uses a processing pipeline concept. meaning that we first define a pipeline and then we execute it. This is a concept which we have adapted from the visualization toolkit. We use a demand-driven execution pipeline, which means that we will only re-execute when needed. For instance, if a parameter of an algorithm changes or if an algorithm receives new input. Here is an example how such a pipeline might look like. You have a processing step which imports some data, an image. You have a processing step, some algorithm that performs some processing using some parameter. And we connect these processing steps using the set input connection and get output ports. And finally, we add a rendering step at the end, which visualizes the data. And here you can see the pipeline where data objects are sent between each processing step. This means a quite loose coupling between the processing objects, which means we can easily interchange these processing objects. The way FAST uses Opencl is that each process object has access to Opencl devices, meaning that it can execute kernels and can request access to data on Opencl devices. It reduces data transfers between CPU and GPU by having almost all the image processing algorithms and visualization algorithms implemented in Opencl for GPUs. And there are quite many of these algorithms that are now implemented and included in FAST. Data in FAST is represented by abstract data objects, which represent some data which can be stored in multiple locations. An image, for instance, can be stored on multiple Opencl devices, both as an Opencl image and buffer, but also on the host as a regular pointer, and even as an Opengl texture. Even though the image is stored in multiple locations, in FAST it is represented as a single data object. The same applies for other types of data such as geometry, vertices, lines, and triangles. These data objects handle data transfers between the different locations. The developer simply has to request access to the data on a specific location. FAST uses lazy data coherency, meaning that when the data is changed in one location, the data is not updated on other locations until it is requested on that location. We argue that this kind of data abstraction makes heterogeneous computing easier by reducing the amount of boilerplate code. In the beginning, there were a lot of frustrating bugs in Opencl implementations. One bug I especially remember was on Apple's Opencl, where a kernel was crashing for no apparent reason, only to work after changing the order of code lines, even though it didn't change the results. Another curious bug was on AMD Opencl, in which machines with regional settings where comma is used as a decimal point instead of the dot, which is the case in Norway where I'm from. Of course, we don't use comma as decimal point when we are programming, but the AMD Opencl compiler for some reason crashed when building Opencl kernels because it was unable to parse floating point numbers. And I still have this piece of code in FAST running at startup, which detects if the decimal point in the current locale is set to comma, and if so, changing it to dot. Here's a piece of kernel code with a hack to deal with the fact that the mix function was missing on Apple Opencl. Now, in 2021, I would say that Opencl implementations have matured a lot. Nonetheless, FAST is still using the now 10 years old 1.2 version of Opencl. This is mainly because NVIDIA is still stuck at version 1.2, and we want FAST to work on all major platforms such as Intel, AMD, and NVIDIA. Hopefully, with the launch of Opencl 3.0, we will be able to get some of the functionality of version 2 into FAST as extensions. But for every extension used, alternatives has to be implemented and maintained if the extension is not supported by all the major platforms. This is a big challenge when working on large software frameworks. Supporting Mac Osx on FAST has always been a challenge due to the buggy Opencl implementation of Apple. I was always hoping this would improve in the future, but after Apple announced that they were deprecating both Opencl and Opengl in 2018, I simply gave up supporting this operating system. My only hope for this operating system now is that we will somehow be able to run Opencl and Opengl on Metal in the future. As mentioned, the big challenge with developing a large framework like FAST with Opencl has always been finding a balance between optimal performance and cross-platform support, low-code complexity, and generality. And we often find that we had to trade performance to achieve these goals. Most medical images are monochrome, meaning that they have only one channel. However, the images come with different precision. For instance, in ultrasound, we typically have 2D data stored as unsigned 8-bit integers, while in CT, it's common with 3-dimensional data stored as signed 16-bit integers, and in MR, unsigned 16-bit integers. Microscopy images, however, are typically color images with RGB channels stored as unsigned 8-bit integers. Thus, FAST needs to handle all these image types with different precision, number of channels, and dimensions. Ideally, every process object in FAST should be able to handle input images with any of these formats. FAST uses mainly the Opencl image data type, since we have seen numerous times that using this data type instead of Opencl buffers improves the speed of many image processing algorithms, most likely due to the texture caching mechanisms on GPUs. A challenge in this regard is that not all Opencl implementation supports all image formats. In 1.2 version of Opencl and earlier, the minimum image formats to support was only 4-channel image formats. In 2.0, this was extended to include single-channel images. So if we have single-channel images on a platform that doesn't support single-channel images, we need to convert when moving data between the host and Opencl device. Now, as you've probably seen, 3D image processing is an essential part of medical imaging. We have a lot of 3D data. And I find it very strange that in Opencl we need an extension to write to 3D images, while reading from 3D images, you don't need an extension. I was happy when I saw that this extension was become core in Opencl 2. I was sad to see it become optional in Opencl 3. Since this is an optional extension, we have to include a backup solution when this extension is not available. Visualization is an essential part of medical imaging. Visualization in FAST is implemented using Opengl 3.3 with some assistance from Opencl. Qt 5 is used to create simple graphical user interfaces and to ensure smooth concurrent visualization and processing, as well as responsive graphical user interface, multi-threading is used, where the main thread performs visualization. An additional computation thread executes the processing pipelines repeatedly, and additional threads are used for things like concurrent data streaming. FAST supports many visualization types, like regular 2D image rendering, which is done mainly with Opengl. Raycasting volume rendering is implemented in Opencl by calculating every pixel of an Opengl frame buffer object. And geometry rendering is done by filling up vertex buffer objects and element buffer objects either on the host or with Opencl, and it's then rendered with Opengl. We also have an image pyramid renderer used for extremely large images, which are larger than the amount of RAM on the GPU. In this renderer, we implemented a virtual memory system which keeps a cache of tiles on the GPU. We also use Opengl texture compression to reduce the amount of GPU RAM used. An important feature in terms of visualization with Opencl and Opengl is the Opengl sharing extension, which enables sharing of Opengl textures and buffers with Opencl. In code, the Opencl Opengl interoperability essentially looks like this. First, you create an Opengl texture or buffer. Then you create an Opencl image or buffer from that Opengl data. Then you perform some synchronization, and then you can do your computations before you give the control back to Opengl again, so that you can visualize the results. One issue with this interoperability extension is its lack of support on Linux. It hasn't been working on Linux with NVIDIA for the last 5 years or so, where you get this error message here. If you know how to get around this error, please let me know. On Intel Linux, it's simply not implemented, but has been requested by many developers on GitHub. Due to this lack of support, FAST needs a backup, which is essentially to perform a data transfer to and from the CPU, which reduces performance. One thing that I've always found strange with this interoperability is that you can only go from an existing Opengl data to Opencl data, and not the other way around. This is counterintuitive in my mind, since you usually do computations first, then visualization. If you don't know in advance which data is going to be visualized, you may either end up creating a lot of unnecessary Opengl data or having to perform a copy. So why doesn't there exist an Opengl extension which allows us to go from an Opencl image or buffer to an Opengl texture or buffer? For instance, a GL function like GL text image 2D from CL, which would allow a more simple code flow, something like this, where you have some Opencl data, and then you simply generate Opengl data from that, and then you can visualize it. This is something I would love to see implemented in the future. These days, deep neural networks have become the standard for most image processing tasks, like image classification and segmentation. So FAST has to support deep neural network inference. But there is no pure Opencl inference engine out there. Most frameworks rely on CUDA and cuDNN. You do have CLDNN, which now is part of OpenVINO, but I think it only targets Intel devices. Also, the world of deep learning is quite fragmented at the moment, with many different model formats and many different frameworks for both training and inference. The solution in FAST so far has been to provide a common interface to neural networks, thus abstracting away all the details of the different neural network APIs out there. We now have support for Intel's OpenVINO, Google's TensorFlow, and NVIDIA's TensorRT in FAST. To facilitate neural network pipeline processing in FAST, we have also made an abstract tensor data object which can store data both as an Opencl buffer and a C++ pointer. Thus, neural network processing in FAST can be as simple as this, where you first have a data source which you connect to a neural network, which simply loads a model from disk, and then you connect the output of the neural network to a rendering object. My hopes for Opencl in the future is that we get a high-performance neural network inference library running purely with Opencl and running on all major platforms. I hope we will see better support for the 3D texture writing extension, which is essential for 3D medical imaging. I also hope we will see better Opencl, Opengl interoperability, and also the possibility of going from Opencl data to Opengl data, and not just the other way. Finally, I hope to support Mac again in the future, maybe with the possibility of running Opencl on Metal. To summarize, we have over several years created a high-performance framework for medical image computing and visualization. Opencl and Opengl has been vital to its success. It's been quite challenging to support all major platforms, operating systems, Windows, Linux, and Mac, as well as Opencl vendors such as AMD, Intel, and NVIDIA, while at the same time delivering high performance. And we see that for every extension we use, it increases the code complexity. Finally, we invite you to test FAST yourself, which is available open source and freely on GitHub. Thank you for your attention, and please don't hesitate to contact me if you have any questions or comments.